Hi everyone, I'm Anders Hejlsberg, Technical Fellow in the Developer Division of Microsoft, and I'm here to talk about a new project of ours called TypeScript. I'm sure you've all noticed that JavaScript has gone through explosive growth over the last 5 years or so. We have gotten much better JavaScript execution environments like the Chakra engine in IE9 and IE10, Google's V8. We've got HTML5 that actually has made the UI really be a very full-fledged programming platform. But the fact remains that writing application-scale JavaScript is hard. JavaScript was really never designed to be a programming language for big applications. It's a scripting language. It doesn't have static typing. But more importantly, perhaps, it lacks some of the structuring mechanisms that you need in large applications like classes and modules and perhaps interfaces. So 2 or 3 years ago, when we were trying to decide where to go next with JavaScript development tools, we sort of took a look around, and we've noticed that a lot of people in the industry, in order to write large JavaScript apps, use tools like maybe Google's GWT or Script Sharp, which is an open source project that uses C#. And common to those is that they leverage mature tooling ecosystems like Eclipse or Visual Studio and give you development processes that work for large apps. And in that sense, it's a step forward to use those tools. But the problem is that you end up writing your app in a language that isn't JavaScript. And whenever you want to leverage anything that happens in the JavaScript community, you have to first go encapsulate it or do whatever. And so you're sort of at an arm's length distance at all times from the eventual thing that you're targeting. So we felt that what if we could strengthen JavaScript with the things that are missing for large-scale application development, like static typing, classes, modules. And that's what TypeScript is about. It's a language for writing application-scale JavaScript applications. Maybe in a little more detail, TypeScript is a superset of JavaScript that compiles to plain JavaScript. So the thing that you end up running when you're using TypeScript is just JavaScript. And the compiler and the compiled code work in any browser, on any OS, in any host. And the compiler and all of the libraries, everything is all open source. So TypeScript starts with JavaScript. Basically, all JavaScript code is TypeScript code. In fact, our compiler passes, I believe, close to, if not 100% of the test262 tests. And so you can simply copy and paste JavaScript code into a TypeScript source file. Also, all JavaScript libraries like Node, jQuery, underscore, backbone, prototype, etc., work directly with TypeScript because it is just JavaScript with some additions. And those additions are optional static types, classes, and modules. And those really are, in my mind, the underpinnings for application scale development. Those are the things that are missing, if you will, when you're writing large apps and trying to structure them, maintain them, and so forth. But the beauty of this is that it's zero cost. All of those additional features compile away in the resulting JavaScript. So there's actually no cost to using these classes or modules. They simply compile to normal JavaScript idioms. And that resulting JavaScript runs, as I said, in any browser, on any host, on any OS. All right, so let's take a look at what that looks like. And I'm going to start with a demo of the TypeScript type system. So let me first paste in a little piece of JavaScript code here. This is just plain JavaScript. You see a function that takes an argument and assigns to a property of that argument, and also computes the sum and brings up a message box. Now, there's something funny about this code. It likely wouldn't work. I mean, you're putting a property on it and you're also trying to add it, so it seems a little suspect. But certainly in here, if I hover, you can see that TypeScript has just determined that X is of type any because it doesn't know any better. And any is basically the type that represents any value in JavaScript. So anything can go into X, and therefore you can access any property on X, you can do any operation on X, and you can pass X as an argument to any function you care to. But let's say that you intend for X here to be a string, for example. What would you do? Well, there are already tools out there, if you take, for example, Google's Closure, that allows you to add annotations that look like this, where you say @param, and you say that X is of type string, and you can also add some documentation for X here. And if you think about it, that's really like a type system in comments, right? But it's a little problematic to have your type system in comments because it's not particularly expressive, and when you get into structured types and types that depend on other types and so forth, it gets rather unwieldy, and also it doesn't look all that great in the code, so it sort of hampers readability. In TypeScript, we instead allow you to simply put annotations on your parameter. So here I can annotate X and say it's of type string. And when I do that, you see that things start to light up. For example, we're now being told here that there's no name property on string because we know that string doesn't have such a property, and therefore we can flag an error. Let me try to get rid of that line. Let's try one of the other primitive types like number. And now we see another error. Well, first of all, we actually see that when I add two X's, I get another X, and so we've inferred that V is of type number. And when we try to pass a number to alert, we get an error because if we look at what the prototype for alert is, it says that it needs to take a string. Let's try the last of the primitive types of JavaScript, bool. And now you'll note that we get an error on the plus operation because you can't apply operator plus to two bools. Well, technically, you can do anything you want in JavaScript, but you're not going to get a meaningful result, and therefore we flag it. So this is all about, in a sense, defining a semantic subset of JavaScript, the subset that makes sense, because JavaScript allows you to do a lot of nonsensical things, and those are the ones that we're trying to catch here. We can also do structured types. Let's say that we say X is a string array, and now if I say X sub 0 dot, you'll see that we get statement completion with all of the methods of string. So we know that we're dealing with an array, and you can index into it. You could also, for example, say that string is X is a function that returns a string. And now, if we call X, the result is a string. But perhaps, more importantly, you can say that X is a type that has a number property and a string property called A and B. And now, if I dot on X, we see that there's an A property and a B property. Now, we might, for example, here change our code to say return x.a. Now, you can see here that types can be just written in place, and we actually have a structural type system in TypeScript. But you can also give types names. So we might, for example, insert a type declaration of an interface, which is just a name, the name that we give object types, called thing. And now we could modify our code here to say that X is of type thing, and you'll see that we still get the same statement completion. There's an A and a B. Let's try to write a line of code that actually calls this. So we'll pass so we'll call the process function, passing in an object literal with an A and a B. And let's look at a few things here. Well, first of all, you see that we've declared A to be of type number, and therefore x.a is of type number. And since we return a number and we don't have a type annotation on the return type of our function, we infer that process is a function that takes a thing and returns a number. And since we're assigning that to n, well then in turn n is of type number. And so you see the types flow here through a process called type inference. And we can actually infer a whole lot of types without you having to write them. The other thing you see is that interfaces are structural. So as long as you have the right members of the interface, in this case a number, an A and a B property of type number and string, well then you can write an object literal that satisfies that interface. Let's try to add an extra member here, for example, C:bool, and we'll see now that we get an error down here because we're missing C from our object literal. And of course we could go add it and that would make the compiler happy. But what we could also do instead is we could say that C is an optional property, meaning that you don't have to specify it. It is still there, so if we look on X here, you'll see that there's a C property, but whenever you use it, you need to first check if it's undefined, because it may have not been given to you. If you do give it down here, things are of course happy, but interestingly, if you give a C property but of the wrong type, then again that's an error. So if a C is there, it must be a bool, is really what we've said. Okay, now of course you can also have functions in interfaces. Let's add a foo function, and now we'll note down here that we now have a foo, and we now get statement completion of foo takes a string, so I can give it a string and it returns a string, so now the compiler has inferred that this guy returns string. In fact, if I add another argument here, you'll also note that we complain if you're not passing the right arguments to your function. But just like properties, you can make arguments optional. So n here is now an optional argument. And now you can either not give it or give it, and we're happy. In fact, in addition to optional parameters, we also support overloading. So I could declare foo to have two possible ways you can call it. Either passing in a string, in which case it returns a string, or you can pass it a number, in which case it returns a number. Now, down here we have one that calls the string version, but if you look, you'll see that there are two options here available, and I could also pass it a number, and in that case, we now infer that our function returns number. So we can do overload resolution on this stuff. Okay. Of course, it's not really possible in JavaScript to have multiple implementations of foo. There's only one, and what we're really just saying here is in that implementation, it is up to the user to ensure that if you give it a string, it should return a string, and so forth. So we're not actually necessarily enforcing all of this, but we're allowing you to write the correct modeling of it. The overloads I just wrote actually correspond to this. What we're really saying is there's a foo property that has two call signatures, one taking a string and one taking a number. I could also add data properties to my foo here. For example, I could say there's also a property called data of type any, and now if I use foo, well, you'll see that it has two overloads and a data property. And this is entirely possible in JavaScript. You can put properties on function objects, and that's really what I'm describing here in this type declaration. Indeed, we really allow you to model anything that's possible in JavaScript. Here I have now said that my thing also has a constructor function that takes a string and returns an element. And if you index my thing, then you get dates out of it. So now I might be, for example, say new x of ABC, and then that returns an element, so now I get statement completion for element, or I could say return x sub 0 dot, and now you see that I have dates in my x. Now you're going to go, that is a very strange object I've defined here. And indeed, this would not occur in the wild, but combinations of all of these features do occur in the wild, and all over the DOM, for example. And TypeScript basically stays very true to JavaScript's type system and just allows you to statically describe anything that goes on in JavaScript. And that's really what the point is here. Okay, let me next try to show you another little example of type inference. Here's another JavaScript function that uses a very common pattern where you declare a local variable and then you write a bunch of local functions that close over the local variables, and you return a little object that has all of those local functions as properties. This happens all over the place in JavaScript. And you can see that from this piece of code, the only thing that I've added to this over standard JavaScript is a annotation here that annotates this argument to be of type number. Other than that, it's just plain JavaScript. Yet from this, we can infer a whole bunch of stuff. For example, the compiler here has inferred that the return statement returns an object that has 3 functions, one called clear, one called add, one called result, and it's figured out what their types are. And so it's also figured out that makeAccumulator is a function that takes no arguments, that returns an object that has those 3 functions in it. And so it knows everything already. I might here then say var a equals makeAccumulator, and now when I say a dot, you see that we now know that there are those 3 methods. I can call them, pass a number, etc., etc. So that's, in a sense, inference going in one direction, where we infer from your code what the types are. But sometimes it goes in the other direction. You might, for example, somewhere have a declaration of an accumulator interface that you are supposed to go implement now. And let's say that this is my function that implements it. In that case, I would typically say my function returns accumulator. And now we check in the other direction. So you see no errors show up because this is actually an implementation of that interface. But let's say I had mistyped something, and now we get an error because this isn't of the correct type. And this is super valuable in JavaScript programming. Imagine that you had a 200-line object literal that you're returning here, and there's something wrong somewhere, but you're just staring at these 200 lines. Well, we will tell you. Okay, another place where that type of inference is super useful is when you're writing event handlers. So let's say in here I'm writing an on-mouse move event handler. So equals function of e, and then e dot. And you'll notice that we know what the type of e is here. We know that it's a mouse event, and it has a client X and a client Y and so forth. And so we can give you statement completion on this stuff without you having said anything at all, really. Because if you hover, you see that we've inferred that it's a mouse event. And the reason we've inferred that is that window declares a mouse event. Now we could actually use the IDE to navigate to that declaration. So we can go to definition on mouse move. And now we jump into a file called lib.d.stir, which is the declaration file for the entire DOM and all of JavaScript's standard runtime library. There's about 8,000 lines of declarations in here. And these are basically just the interface declarations of everything that's in JavaScript. And I don't think anyone can memorize these 8,000 things, but the compiler can and just present it to you whenever you need it. And that's what makes this super valuable. For example, if we go to mouse event here, we can just navigate around in here and find the declarations of everything. And you could even modify this file if you're in a different browser that has different additional capabilities. Okay, so that's a quick tour through the type system. Let me just summarize here that what TypeScript does is it basically formalizes a static type system that describes JavaScript's dynamic types. But it describes them at development time, and then it can offer excellent tooling on top of that information. You see that we do a lot of type inference and structural typing. It's actually remarkable how few type annotations you need to add to your code to get all this machinery working. TypeScript works with existing JavaScript libraries. You saw that you can write declaration files separately from the libraries that you're trying to provide static typing for. So things like Node, jQuery, Prototype, underscore, well, some of them we've already written the declaration files, but anyone can write these declaration files, and once you do, the whole system lights up. Final thing, this type system is not provably type safe. talk to the type theorist. But then again, most type systems aren't. Like C is not provably type safe either. But what it allows you to do, though, is allows you to state the intent in your code and have the tools check it for you. But once you compile, all of that goes away. And it's just JavaScript. And it'll do whatever JavaScript would do when you write the particular code. So we're just aiding you at development time. OK. So let's try and take a look at some of the other features in TypeScript that allows you to do structuring of larger applications. I'm going to go to Chrome and just show you that TypeScript works in any browser. And I'm going to go to our playground. And our playground is a place where you can type in TypeScript code and see the translation into JavaScript. And so we're going to take a look at that here. I'm going to start by typing a class, point. And then in my point, I'm going to declare x:number and y:number. So two fields, x and y. And then I'm going to make myself a point. Oops, new point. There. And now you'll notice that when I type p dot, I get statement completion on my point. There's an x and a y member, so I can say p dot x equals 10 and p dot y equals 20, for example. And if you look at the code, you'll see that we've just produced idiomatic JavaScript here. We produced a function closure that contains the constructor function, and that's what we return out. Now, typically, you would want to have the ability to pass arguments to your constructor. For example, you would probably want to say, give x and y for my point. You'll note that we complain here that we say, well, this doesn't match the supplied parameters. Well, because we haven't written a constructor yet, but let's write one. So constructor of x:number, comma y:number. And in here, we will say this dot. And again, you'll see that we know that this has two fields, x and y. So this dot x equals x. This dot y equals y. Now, this class syntax here is very aligned with ECMAScript's 6 proposal for classes. Of course, on top of it, we've added type annotations. That's what TypeScript adds. But we, in all of our additional features, are working hard to align with ECMAScript 6. Even as that standard moves, things will probably change here as well. So you see in here how we now initialize x and y on our object. We can, of course, also write methods. Let's write a distance method that returns the length of the vector given by our point. So square root of this dot x times this dot x plus this dot y times this dot y, like so. And now if we go down here, you'll see that if I say p dot, we get statement completion that there's a dist function that returns a number. If you look at the generated code, you'll notice that we initialize properties on the instance of point, but we put methods on the prototype of point, and that is precisely what ES6's class proposal does as well. We actually support accessor properties too. So if you're running in an ECMAScript 5 compatible browser, you might want dist to be a property instead of a function. And you can do that just by making it into an accessor. And you'll see that the generated code then shifts around and all of a sudden now becomes an object.defined property of dist. And you'll notice that in statement completion, we now have a distance property, not a method. There. We also allow you to declare static properties. Static origin equals new point of 0, 0, for example. And you'll note that in our generated JavaScript, static properties go on the constructor function object. Methods go on the prototype. Properties go on the instance. So we put everything where it's supposed to go in JavaScript. In fact, now if we look, you'll see the point now has two members. There's the prototype that is on every constructor function, and there's the origin static member that we just introduced, which is itself a point. In fact, if you hover over point here, you'll see that we know the type. Point here references the constructor function, and it has a point an origin property and a constructor signature. And then point also is a type, the type of P. So there are 2 points in there, a constructor function and an instance type. We also support private members. Let me try to add a private color :string here. And you'll note then that inside the class, I now have a color member of type string. So I can say color equals red. But outside the class, there is no color. So privacy is basically the ability to restrict access to certain members. But again, this restriction, if you look at a generated code, there's really nothing special about color. So this is all about stating and enforcing your intent at development time, but producing normal idiomatic JavaScript. So there is no notion of private properties in JavaScript, and so we generate the best we can here. Now with ECMAScript 6 and private names, we may be able to do a better job, and once that comes online, we can retarget or have a compiler option to do that. Okay, a couple of other nice features. You notice that this pattern of declaring properties X and Y and then initializing them in a constructor is very, very common. And we actually have some syntactic sugar that allows you to shorten that. So I can get rid of those, and then I can just declare automatic properties in my constructor arguments, and you get the same effect here, that we automatically declare a property called X and initialize it with the X that you gave to the constructor. In fact, we support for functions and constructors default values, which is another ECMAScript 6 feature. So you can give the default value here, 0 for example, and you'll note that we generate code that puts that default value into your argument if the values weren't given. And now the type checker also knows that it is not an error to omit the arguments from the constructor code. Now, classes, of course, also support inheritance. Let's try to write a derived class point 3D, extends point. And let's just pause here because a whole bunch of code got generated for that, and let's take a look at that. You see again that we have a point 3D, but since it is a derived class, we now pass in a base class as a super argument in our function closure. Then we call a helper function extends, which we inject into the generated code only if you have derived classes. And I should say that this is the only time we will inject code into the generated JavaScript other than the code that you wrote. And here we then do whatever gymnastics is necessary to set up the prototype chain. And then automatically we emit a call to the base class constructor if you don't actually write a constructor yourself. But let's try to write one here where we say, for example, our constructor has, there. I don't think I got that right, did I? Oops, semicolon there. My constructor has an X and a Y and then a public Z member, and then inside my constructor, let's just call the base class constructor like so with a super call. And I can also in here put in, for example, an override of the dist method. I might say var d equals super.dist, so call the inherited method and then return math.squared of d times d plus this dot z times this dot z, for example. So classes with inheritance. Let me try and show some of the other features that are in here. In fact, let me just go grab a little code snippet from over here and paste it in. Here's a little class called tracker that has one property in it called count, and then it has a method that starts it. And in the method, we just attach an onMouseMove event handler where we handle all mouse moves, and for every mouse move, we increment our counter and write it out to the console. Let's try to run this code. And let's try to bring up the F12 tools and look at the console window, and we'll see that there's something going on in here. We're just getting a bunch of nams, so something went wrong. The thing that went wrong is the thing that goes wrong very often in JavaScript, which is you have the wrong this. When window.onMouseMove calls your event handler, it passes the element that you're over as the this pointer. It doesn't pass the the place that you were defined. Now, if we had actually typed this code in, we would have discovered that, because if I hover over this here, you'll see that this is of type any, and we wouldn't have gotten statement completion and whatever. So you know, we would have noticed, but let's say we hadn't. Now, this is so common in JavaScript that in ECMAScript 6 there's a proposal to introduce what's called arrow functions, or also known as lambdas, from languages like C# or for example. And they use the fat arrow syntax. So I could instead write my function here, or my event handler, as an E arrow and then the same code. Now, the thing that's different about arrow functions is that they have a lexically scoped this, which means they have the same this as their surrounding function. And the way that you make that work is you have to capture that out of this and then reference it inside with, and people often write var that equals this, and then inside their method they use that dot instead of this dot. But you'd notice that we can just do that automatically for you. We can emit that code. Now, if I run, you'll see that my sample now hopefully works. Yes, I'm actually working on the correct this. If you look at the generated code here, you'll see that we captured the outer this and then rewrote all of the references to be that outer this instead. The thing that's interesting, by the way, is that we will only generate that if there are references to the outer this. So notice what happens here. If I backspace here, it disappears because I'm no longer referencing the outer this in my lambda. So we'll only generate these closures if we actually need to generate them. So that's arrow functions. Another feature that we have in TypeScript that's inspired by ECMAScript 6 is modules. And let me start by showing you what we call internal modules, which are modules that are local in a source file. I could, for example, create a module utils and put my tracker class into that module, like so. And then I could export my tracker out of that module. And you'll notice that the code we generate is a function closure that contains our class declaration, and then we assign all of the exported properties onto the object that represents the module. This is a very common pattern in JavaScript. Of course, now you'll see that our tracker isn't there, but it is indeed now inside the utils module. I can actually sort of nest arbitrarily. Well, I should mention that modules are open-ended, so I could write another module utils here with an export var greeting equals hello, for example. And now you'll note that if I say utils dot, there's now two members on it. There's a greeting and a tracker. But imagine that these two modules were in separate source files. So modules are, in a sense, also namespaces that are open-ended, and different source files can contribute members to these modules. And the code we generate allows you to do that. I might also, for example, deeply nest something, and you'll notice that we generate then multiple function closures. And now, of course, this thing ends up with a very sort of unwieldy name. But if I hover, you'll notice that we know that this guy's an Acme core utils tracker. I could shorten the name by using an import. So I could say import ACU equals acme.core.utils. And then in my reference here, just reference acm.tracker, for example. And over here, you'll note in the generated JavaScript, an import is simply just a local variable that references that inner module. So that's internal modules. The other kind of module we support are external modules. Now, to demo those, let me not save that, and then let me go and grab a blank file called server.ts here. External modules, we support two models for external modules based either common JS modules or AMD modules. So common JS modules are the types of modules used by Node.js. And basically, a module in Node or in common JS is a JavaScript source file. A module loader arranges to load that module along with all of its other requirements, and then you can export members out of that module. And then there's AMD modules, which are built on top of common JS to provide an asynchronous module definition for modules in the browser. And we support generating code for both of those. Let me show what it looks like. I'm going to try to write a little multi-module Node application. I'm going to have a server module and a hello module that uses my simple server module. So in my simple server module, I'm going to start by referencing the static types for Node.js. And the way I do that is I just simply put a reference in my file. And now I can actually navigate to this file. And in here you see the static types that are declared for Node.js, including, for example, zlib, HTTP, et cetera, et cetera, et cetera. OK. In here, I might then say import HTTP equals module of HTTP, like so. And now I actually have a reference to the HTTP module from Node. And then I might write an exported function, export function simple server port colon, oops, number comma message colon string. And in my simple server, maybe I'm going to do something with HTTP. And you see here now we get statement completion on the HTTP module in Node. So I can call http.createServer. And it tells me, well, in Node, createServer takes a callback that requires a request and a response parameter. And now in here, I can say response dot, and again, you'll see that we have picked up what the types of those are from the definition of the create server module. So lots of type inference happening here that automatically flows the types. Let me just, so you don't have to watch me type it here, let me just paste in the code that I want in my server. I simply want to write out a hello world message. And then finally, I want to start the server by calling its listen method. And again, here you see we get statement completion on that. So we'll just listen on the port that we give. And now I have a super simple little module that has one function exported in it called simple server. So next, let's try to grab another empty file here called hello. And then let's try to use the simple server that we just wrote. So I'm going to say import server equals module of ./server. So now I import the module that I just wrote, and then automatically I get statement completion on the code that I just wrote. So that has automatically become part of my compilation here. And now I can say listen on port 1337, and the message is greetings channel 9, for example. And finally, let's just say console log of listening there, and save that. So here we have our two module project. Let's go to the directory where I put these files. You'll see that we have hello and server.ts and the static typings for Node. We can now use the TypeScript compiler to compile hello.ts. And you'll note here that I don't have to give it all of the files. It will automatically figure out the dependencies from the imports that I had and the / references. And so we automatically you just give us the top file and we figure out what everything is. And you'll note in here now that we have two JavaScript files, hello.js and server.js. We could even look at, for example, our hello file. And you'll note that it is very, very simple too. What I type, my module import has turned into a require, but other than that, it's the same code. And I'm good to go now. I can start my hello app. And now let's go to, let's see, localhost 1337. And here's our little greeting from our little node server. So very simple stuff. Okay. Let me just summarize here. Classes and modules basically are the building blocks that allow you to do scalable application development in TypeScript because they enable you to define and maintain clear contracts between different parts of your application. We're working very hard to align with the emerging standards for this stuff. So class, module, arrow function syntaxes are all borrowed from the current ECMAScript 6 proposals, and we will continue to align with that. And you saw that we support the popular module systems that are already in use in the industry, like CommonJS and AMD. And let me now, for the final little section of demos here, show you some of this application scale in action. So we're going to go back to Visual Studio here, and let's try to pick up another file. We have one of our samples is called ImageBoard. I'm going to load the main application in ImageBoard here. And you'll notice that this is a Node application. We reference Node. It also uses MongoDB, and it uses Express with Node. So there's a database module that I wrote here, and I can go to definition on that guy. And you'll see that my database module is a wrapping around Node, so I can go in and actually look at the static typings for Node. These are not entirely complete yet. This is stuff that's still in flight, but you get the idea. In my database module here, you'll note that we use the Node APIs, but we also declare some interfaces that represent the data entities that I'm storing in my database. And that actually ends up being very, very convenient because now whenever I use the entities, I just automatically get statement completion on what the properties of those guys are. So we have users, boards, images, you can see. And then we have some accessor functions like getUser that just wraps around the necessary calls to put them into a MongoDB table. I could actually do a find all references on my getUser here and see all the places in my app that I'm using this method. And you'll note that there's the place where I declare it. But then there are two places in the app where I call getUser. And let's go to this one here, for example. And you'll note here that we actually are tracking all of these different modules. So there's an app module, which is actually came from Express, the Express module. Oh, sorry, there's an app object which came from Express and is of type Express server. There's request and response parameters that came from Express. There's a user parameter that came from the database encapsulation that I wrote. And in here, if I reference user dot, you'll see that I get statement completion on the types that I just wrote in my database encapsulation. Let's try to just look at what it looks like to run this guy. So here's the code. We could compile it, app.ts here, and we'll look. That produced a couple of JavaScript files, one for app and one for the database. We could then start up MongoDB in a separate process here, and then we can start up Node on our app, and then go to port 3000 on our local host. And here you see the ImageBoard example, and it's basically a little app that allows you to pin up pictures in some collections. You can have different users, and they can each pin up different stuff. Here's another one for Luke. Luke likes flowers. We can add new pins, etc., etc. So a simple little app, but it shows you multiple modules running on the node. Okay, another app I wanted to show is an app called Warship. Here we go. This is an app that uses jQuery, and it also uses jQuery UI. If you look at the static typings here, you see that we just reference the declaration files for jQuery and jQuery UI. If we go to our Solution Explorer, one thing that actually I haven't even gotten around to mentioning yet, if I just get rid of these guys here, is that we automatically infer projects. So when you open a file, pretty much anywhere, oh, I closed the wrong file, sorry. Because Warship references jQuery and jQuery UI, you see that we automatically infer a project consisting of the Warship file and the two declaration files and the one that declares everything for the DOM. And we do that by traversing all of the references that are in there and all of the module imports and exports, and then finding the entire app automatically. So you can sort of start anywhere and you automatically are in the right project context. Now if we look at jQuery, in fact, one way to look at it is just to type in $, so that's the jQuery object. You see that we get statement completion for all of the various things you can pass to it. Let's say $, of div dot, and then you see all of the jQuery methods like @class, for example. And now we can actually go to the declaration of that, and you'll see that we are now in the jQuery module, and here's the @class method. In fact, there are two of them. It's overloaded and can take different arguments. But this gives you the static types for jQuery. But then the really interesting thing is that jQuery UI builds on top of jQuery by adding new members to $. And in fact, we could look at $, of div dot draggable. And if we go to definition of that guy, you'll note that that's in a different file. That's in jQuery UI, which declares additional members in the same interface. So in TypeScript's type system, interfaces are open-ended, and multiple entities can contribute to an interface, and that allows us to accurately model what very often happens in JavaScript, which is that one library builds on another by adding new members to its global object or its representation. Okay, let's try to go here and just quickly compile the Warship app, and then let's try to run it. And this is basically like battleships in here. I can, start shooting, and let's see if I got a couple of good hits in already. And basically, but you can have fun with that app. Okay, last thing I wanted to show is the TypeScript compiler itself, which TypeScript is written in TypeScript, and since it's open source, we actually give you the entire source code for the compiler. And let me try to go load up some of it in compiler here, and we'll just grab a random file, AST. This so happens to be the file that defines the abstract syntax trees for everything. So we can go look at, here's the class that represents case statements in the compiler. You'll note that I just grabbed one file out of the compiler, but we have already inferred the entire solution for the compiler because we follow all the references. So if you go up here and you note that we reference typescript.ts, and if we go open that file here, you'll see that that's the main compiler file, which in turn references all sorts of other files, and by tracing those, we automatically see the whole picture. The TypeScript compiler declares a class called TypeScript compiler. We could try to look at that. Here you see that the compiler instantiates a parser. So we can go look at a parser. The parser in turn instantiates a scanner. This is a very nicely layered compiler. And in the scanner, there's a property called line, which is the current line number that the scanner is processing. Now, we could find all references to line in here. And here you see that, well, there are a bunch of references in the scanner itself, but there are also some over in the parser that references that property. Now here in particular, there's one interesting reference. If you look, here we're referencing scanner.line. But above it, we're also referencing a .line property on a different object called lineCall that isn't related to scanner. Now let's say I wanted to rename line from the scanner, but I don't want to rename all the other line properties in there. How can I tell which line is which, so to speak. That's very, very hard to do without static typing. But once you have static typing in place, it's trivial. It's what the compiler does all day. So we could, for example, try to grab this parser here and put it down at the bottom. So we can see this code here. Here's our scanner.line. Here's the other reference to .line. Then let's go back to where line is declared in the scanner up here. And now let's try to rename line. And we'll instead call it line number. And now when I press enter, you see one of them renames, but not the other, because we know which one you're talking about. So if I undo, you can sort of see here, these guys change, but this guy up here stays the same because it's a different property that so happens to have the same name. Now this is the kind of thing that makes very large JavaScript applications very hard to maintain. And that's why tooling really, really helps. Okay, final thing I want to show is actually that we can compile the compiler with the compiler. I might go into the compiler directory and say, compile TypeScript, producing an output file, ts.js, and also generate a declarations file. And we'll look at that. And then I want to compile TypeScript.ts there. That's going to produce two files, ts.js, which is the compiler itself, and then it produces a declaration file for the compiler. So you see the compiler itself is 1 megabyte of JavaScript. And now you can take that JavaScript file and run it through your minifiers and all your other JavaScript toolchain. But we've also produced a declaration file that is basically a summary of the external interface of the compiler, if you will. If we start that up, you'll see that, let's grab this guy and put it up here so we can see the whole file. Get rid of this guy. And here you see the file that we've generated is basically a summary of the entire compiler. In here you see, again, all of the ASTs and whatever, but the code bodies are gone. Now you can take this declaration file and you can now continue the next level up the chain of your modular development, where you just treat the compiler as some component that you're already done with. Now you're just taking its external interface. So you can see how we can automatically generate these declaration files, or you can hand author them if you're trying to encapsulate or describe an already existing JavaScript library. Okay. So what's included in TypeScript is an open source compiler and language service, all written in TypeScript. We include tooling for Visual Studio that gives you a language service in VS, but like I said, all of the services that underpin that are open source, and anyone could use those to produce their own development experiences. We have a browser-hosted playground that you saw me play with. Lots of libraries with static typings of the DOM, jQuery, Node, etc., etc. And then, of course, lots of samples and also a formal language specification. So, as I started out by saying, application-scale JavaScript development is hard, but as I think you've seen, TypeScript makes it easier. Please check it out at typescriptlang.org and let us know what you think. Thank you.